I'm going to do another friction example. Now the last friction example that I did was a very simple case. I did use a pulley, so I guess there was that, but it was a block, flat table with a triangle mass hanging down. Now what I would like to do is look at the same thing on an incline. So let's give this thing an angle of, I'm going to go with 37 degrees, just because it has a really nice sine and cosine. And there is a triangle mass hanging down. I would like to know a couple of things. Here we go. What's the minimum mass of the triangle needed to keep the block from sliding down the ramp? What's the minimum mass of the triangle needed to get the block sliding up the ramp? And once the block does start moving up the ramp, what's the acceleration? So first things first, I'm going to free body diagram this thing for the block. I have a ramp that looks something like that. So the forces that I have on this block, I've got mg going down, I'm going to call that m1g. I've got a normal force going this way. I have a tension force going up the ramp. Now the first question is, what's the minimum mass of the triangle needed to keep the block from sliding down the ramp? So the block wants to slide down the ramp, which means my static friction is going to have to go up the ramp. Okay, this is a problem where all my motion is along the ramp. So I'm going to say, let's let this direction be my positive x, which means that direction is my positive y. Then I'll put a box around this thing and call that my first free body diagram. For the other free body diagram, I have this x-axis that points up the ramp, and then it hits the pulley. So my x-axis here has to point vertically down. I have the forces. I have mg going down. I have T going up. This is for a block with a mass of m, and there's nothing else. There's no friction, there's no normal force. I'm not up against a surface or anything like that. So I'm going to call down my positive x direction, and that means to the right is going to have to be my positive y direction. And that's where I am for my second free body diagram. Onward. Looking at my first free body diagram, I'm going to have to break a vector into components. X is along the ramp, y is perpendicular to the ramp, gravity is neither along x nor along y, so I'm going to have to break that up. I'm going to have this side, and I'm going to have this side. And the angle of the ramp, that's got to be the angle inside this triangle. So this side is going to be an mg cos theta. This side is going to be an mg sine theta. Here we go. I'm looking first for the minimum mass of the triangle needed to keep the block from sliding down the ramp. So maybe I start with the triangle. Sum of forces in the x direction. I've got mg going down the ramp. M is an unknown, or going down, just down, minus the tension, which is up, equals ma, and that's acceleration in the x direction, but if this is going to just barely not be moving, that's going to be 0. So I have one equation, but it has two unknowns. I'm going to have to go with the block. I guess I could say this one was my triangle. For the block, looking in my x direction, I have t going up in the positive direction, plus fs, minus mg sine theta equals ma. I am also going to have to plug in what this fs is. If I'm looking at my threshold case, fs max is going to be mu static times the normal force. I don't have the normal force yet. Y direction to find the normal force. I have the normal force up. I have mg cos theta down. And together that equals mass times acceleration in y. Acceleration in y had better also be 0. Just like that guy was 0, this was an acceleration in x. So what I have is that my normal force is equal to mg cos theta. All black letters, this is good news. I'm going to take that and plug it in here. When I do, this equation becomes t plus fs, which is mu s times the normal force. Normal force is mg cos theta. These are all m1s because I'm dealing with the block. The other one I called a capital M, so it's fine either way. T plus fs. This whole thing was my static friction. Minus m1g sine theta equals m1 times ax, which is 0. Next, the only unknown I have in here is tension. Tension equals, if I solve this thing out, that. I'm going to factor out the m1g just because it's going to make it a little bit faster for me to plug numbers into if I have fewer numbers to plug in. And because I'm looking ahead a little bit, there is my tension. I'm looking for that m, so I'm going to take this whole thing and plug it in for tension. I'm going to come back and explain why I'm not plugging numbers just yet, but let me do that. M times g minus m1g sine theta minus mu s cos theta. Remember, this whole thing is my tension force. Equals, and the right side of this thing is 0. So, mg, that, and solving for m, I can just cancel out a g. Now I've got something where I know I could have plugged in numbers sooner, but I didn't, and it was on purpose. Here's why. Well, almost here's why. I'm going to plug in my numbers now. Sine of 37 degrees, that equals 0.6. Cosine of 30 degrees equals 0.8. 0.8 times 0.5 is going to be 0.4. 0.6 minus 0.4 is 0.2 times 10. That is 2 kilograms. There is my mass. Second question. What's the minimum mass of the triangle needed to get the block sliding up the ramp? When I do this, the only thing that's changing is that now my Fs is going to point down the ramp. So purple for question 2. If my Fs points down the ramp, it doesn't affect my triangle equation at all. It makes my square equation in the x direction different because now this is a negative number, this Fs. I'm going to follow that through. If that's a negative number, then this one is negative, which means effectively wherever I see a mu s, I'm going to flip the sign on it. This becomes positive, this becomes positive, 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 and I am in business. Now, 0.5 times 0.8 is still 0.4, plus 0.6 is 1, times 10, that's 10 kilograms, and I didn't have to re-solve the problem. There's my answer to the second question. Last thing, and I'm going to pause for one moment and say this. If that didn't immediately click for you, then go back and re-solve this problem all the way through. Make new free body diagrams, go through all the equations and do it again, and you will get that same 10 kilograms. I looked at it and said, if I wait to plug in my numbers, it's going to save me time in the long run. If you plugged in your numbers right away, then run back through it and do it again. It's completely fine. Not a big deal. It's just its own thing. Once the block starts moving up the ramp, what is the acceleration? Okay, I did this before. I said let's take the exact same stuff I've got and figure that out. So I'm going to try that here. I'm going to see if I can tweak what I've got to get there. I'm looking at the purple one because now I'm accelerating up the ramp, and I'm going to replace static friction with kinetic friction. My triangle equation is going to stay exactly the same, really. The triangle doesn't care whether I have static friction or kinetic friction. It doesn't care about much. So there's that. But now my acceleration is not going to be 0. For the square, I'm going to have the same thing going on in the y direction. Exactly the same thing going on in the y direction. So I can keep all of that. Will be exactly identical. The y direction didn't involve friction at all. So that is for my square. The x direction, that's where things are going to change, but not much. I'm going to grab my same x equation. I can even grab that piece because it's close to true. I mean, it's true, it's just not helpful anymore. Okay, same equation, but my F static has become an F kinetic, so I can't really keep that. So I'm going to have a minus F kinetic. My acceleration is not 0, so let's get rid of that. And I am no longer looking at static friction, I am now looking at kinetic friction. So there's that. Same exact equations, pretty much. I flipped a sign and I changed an S to a K, and that's really all I did. I'm going to plug all this stuff in. Now my mass is a known quantity, so I can leave that in there. And that's it. I'm going to plug in right here. My acceleration is an unknown. So this top equation becomes mg minus t equals m times a. And the bottom equation becomes T minus F kinetic, which is mu kinetic times normal force. Normal force was m1g cos theta. And then minus m1g sine theta. This whole thing was my kinetic friction, equals m1 times A. I'm going to do the same thing I've done a bunch of times. I've got T and A as two equations, two unknowns. I'm going to take these equations and add them together. mg minus T plus T, that's pretty promising, minus mu k m1g cos theta minus m1g sine theta equals m times A plus T. I've got a minus T and a plus T. Those can cancel. I'm going to factor out on the right side. Left side becomes, and then the right side is m plus m1 times A. So A is all that divided by m plus m1. Then I can just plug in some values. I'm going to move this up. Okay, I'm going to write down these values nearby because I find myself kind of going back and forth anyway. That's 10 kilograms. My angle is 37 degrees. My coefficient of kinetic friction was 0.4, and my mass 1 is up here somewhere. 10 kilograms. So now I can plug in. My acceleration will be, and all of that, let's see, this is 100 newtons. Cosine of 37 is 0.8 times 0.4 is 0.32 times 100 is 32. And then sine of 37 is 0.6 times 100 is 60. So 100 minus 32 minus 60, 100 minus 92, that's 8 newtons left on top, divided by 20 kilograms. 8 over 2 would be 4, so 8 over 20 is 0.4. 0.4 meters per second squared is going to be my acceleration.